Welcome, everyone, to our Waste to Wisdom webinar. Today we're talking about biochar production using forest residuals. We really appreciate you taking the time to join us today. My name is Tom Waddell, and I work with Craig Rawlings at Forest Business Network. Our company is a partner in the Waste to Wisdom project, and we're in charge of outreach, and you'll get to hear a little bit more from Craig here at the end of the meeting in the Q&A portion of the webinar. Now, if you have any issues with sound or any technical problems, please use the chat section to the right and type your questions in there. I'll be happy to help you out as best as I can. If you have any questions of the presenters, be sure to look for the Q&A box right down in the bottom right. You can type in your questions there. And keep in mind, though, we will most likely not be able to answer those questions until the official Q&A portion at the end of the meeting. Now, we've got a great lineup of speakers today. We're going to, here, let me switch the slide here so you can see our presenters. The Schatz Energy Research Center is just a fantastic unit there at the Humboldt State University. Arnie Jacobson, the director of the center and also a professor at Humboldt State, will be speaking today. David Carter, a senior research engineer, and then Mark Severy as well, a research engineer there at the center. So looking forward to the presentations today. And without further ado, I think we'll get started, and you'll be able to hear from Arnie Jacobson first, and he'll start the presentation on biochar. Just 1 second.
Thank you, Tom, and thanks everyone for joining. As Tom mentioned, I'm Arnie Jacobson, and I'll be kicking things off for the session and providing a bit of background about the Waste to Wisdom project and our specific focus on biochar for this particular webinar. Then my colleague Dave Carter will spend a fair amount of time focusing on biochar machine testing, including objectives, methods, and results. And then Mark Severy will pick things up and present a little bit related to machine testing, but focusing especially on system integration concepts, challenges, and future work. So without further ado, we'll dive right into the session. Just giving a bit of overview about the Waste to Wisdom project. The basic idea behind this project is that in both forest logging operations and also in fuel reduction efforts, brush clearing related efforts, there's a huge amount of forest residual that is generated, and that ends up being an underutilized resource that could be utilized both as an energy product and for other applications. But transportation costs are very high for moving that material out of the forest. And so our research is really focused on trying to understand ways of overcoming those barriers, either by decreasing the cost of transporting the material or by increasing the value of the residuals before or after actually transporting them in order to overcome some of those costs. And our effort focuses on doing that through a variety of pathways. In the context of the particular work that we're doing, we're looking at biomass briquetting, biomass torrefaction, and biochar production. So those are 3 different conversion technologies and 3 different end products, all of which are higher value end products that can bring additional market value to the process. And so that's part of what we're focused on is that those conversion processes that lead to those higher value products, and then part of it is linked to trying to figure out how to manage the collection costs and the transportation costs. And so if we're able to, one way of doing that is by looking at utilizing those conversion devices in areas that are relatively close to the points of its extraction to minimize the cost of transportation of the very low bulk density material, converting it into a higher value and also a higher bulk density material that can be transported out of the forest. The project as a whole can be divided into 3 different areas, and there are 3 different teams that are working on those. One focuses on feedstock development, and that work is led by Dr. Hansa Pan of the Forestry Department here at HSU with a number of partners, and they're focused especially on production of high quality feedstocks and logistics related issues that can with the intent of bringing down the cost and increasing the efficiency of that collection. The second group is focused on biomass conversion processes and producing those products, and that's the group that we lead here at the Schatz Energy Research Center. And there we're looking at 3 different biomass conversion technologies, as I just mentioned on the last slide, for briquetting, torrefaction, and biochar production. And then there's a third group that is focused on a variety of different analytical tasks associated with financial and economic analysis, social impacts, and life cycle assessment of environmental issues, as well as a few other key processes. The feedstock development group hosted a webinar last month. We're doing one now today, and there will be a third webinar focused on some of the analytical tasks sometime in the near future. This webinar, of course, is focused on biochar, and so the piece of the work that we'll be presenting, it will be looking at the conversion device performance for biochar production and a variety of related issues associated with that. Just briefly, biochar is of interest to us because it has a number of different uses and benefits. It can be used in water and soil remediation related efforts. It can be used as a input for the production of activated carbon filtration systems. It can be used as a soil amendment, and we're interested in all of those different applications. And as a soil amendment, there are a number of different benefits, some of which are listed here. And there are also climate-related benefits associated with biochar production. And so for us, this particular product is a very interesting one in the portfolio of work that we're doing. I'm going to now pass it over to my colleague, Dave Carter, who will talk about some of the biochar production process work that we've done and conversion technology testing.
Thank you, Arnie. We'll start off by looking at the process of biochar production in a simplified fashion. Biochar is produced through the thermal decomposition of biomass in an oxygen-limited environment in a process known as gasification. And on this slide, you can see we have the fuel, the biomass fuel. We're controlling the amount of oxygen that's provided to that fuel and heating that fuel to initiate this gasification process, which then yields syngas and tars and biochar. And so we are seeking to optimize the production of the char portion of this process. This diagram shows the simplified process for the machine that we have tested under the project. Is manufactured by Biochar Solutions Incorporated. And as you can see on the slide, in item number 1 is the main reactor. Feedstock is introduced to the reactor. This is where the gasification process occurs. And in the second process step, the biochar is conveyed from the reactor into the char separation box, also known as the drop box. That process is driven by a large syngas blower that draws air from the reactor into the drop box. The char is knocked out and collected on the bottom of this chamber and then conveyed via a cooled auger to the char collection bins, which are shown as item 4. The syngas is, as I said, drawn through the syngas blower and into the flare, which is item 3 on the schematic. There is fresh air injected into the flare as well to aid with combustion, and the result is an exhaust gas stream which is released to the environment. Here is a picture of the actual machine that we have been testing. This is as it sat in Pueblo, Colorado in July last year, right before we began our testing. On the left is the feedstock hopper, where we load up the biomass, and then the biomass is then pushed onto the conveyor and conveyed into the reactor, where the process of making char starts. The next slide shows a different view of the process. On the left is the other side of the reactor, and you can see the separator or drop box there as well, and then the large syngas blower that draws the syngas out of the separator into the flare. You can see the control panel, and behind the control panel you can see the cooled auger, which conveys the char from the bottom of the separator up to the right end of the machine where that orange motor is. That's the char collection area where char is collected into 55-gallon barrels. And this machine is also fitted with a heat exchanger, which you can see on the top of the flare. There is another large blower that blows fresh air through the heat exchanger on the flare, and that is heats the air that is then used for drying of the feedstock. So the goals of our testing are listed on this slide. We were interested in developing feedstock quality specifications, so testing different types of species with different moisture contents, different particle size distributions, and different ash contents. So we developed a test matrix, which I'll show you in a minute, and we ran a series of tests measuring the consumption and production rates for the different feedstocks. We documented the operational intensity and labor requirements for each of those feedstocks, and we also determined the energy requirements and collected data to analyze and assess the environmental impact and fire hazards associated with this process. The image on this slide shows the machine as it sits in Branscombe, California today, where it's being used by the Redwood Forest Foundation for commercial production of biochar to fund its restoration efforts in the Usal forest. Next, this slide shows our feedstock test matrix. In the first row, you can see the species that we tested. The second row shows the combination methods. Third row shows contaminants. We did deliberately add contaminants to some of our runs in the form of tops to simulate a slash pile, and then also just straight up soil. We had contaminant levels that were high by default in the juniper that we tested, just because it had a high level of contamination as received. The fourth column shows the moisture contents. You can see we did a variety of different moisture contents, and then the fifth column shows the ash content, and the fifth row shows the ash content, and the last row shows the particle size distribution. The red boxes are here to highlight sort of some of the key talking points that we wanted to discuss today. On the left, the conifer, you can see the moisture contents and the ash contents and particle size distribution there in that box on the left. They were, this is sort of an ideal type of a feedstock we found for the machine, but I use that term sort of loosely. It ran very well. So this is a sort of a sweet spot from our testing. The next box, the one that's in the middle, shows the high moisture content runs that we did, and you can see we did some very high moisture content, 37% and 25%. This chip was very uniform. It was, I believe it was called playground chip, so this is a very uniform feedstock, but it was very wet, and that was, we were able to make char, but it was very challenging to operate the machine with feedstock that was that wet. And then on the right, that box shows the high ash content that we observed in the juniper that we tested. And you can see those ash contents are very high. We were able to run and make biochar. However, we did see a marked increase in the amount of clinkers that were generated, and that led to a significant increase in operator input to keep the machine running. Okay, so getting into some of our results, looking at the throughput rates on an as-received basis, we found an average throughput of 380 kilograms per hour on feedstock input, and an average of 43 kilograms per hour for biochar production. You can see the range here in the graph, in the chart, for the brown being the feedstock and the gray being the biochar. We saw an average yield of 12% by mass across all of our runs. And we want to point out that these results are slightly skewed because they don't account for the biochar quality. So, for example, the pinyon juniper ground looks really good in terms of the yield. It looks like we had a really high yield on that, but in reality, most of that was ash content. So the quality of the biochar was low, but the yield looks really good. So a thing to note there is that for commercial purposes, you want to understand the ash content of the material that you're buying or selling to make sure that you're actually attributing the value to the fixed carbon, which is what's most valuable in the product. And on that note, so we looked at the fixed carbon throughput rates across all of our runs. And fixed carbon is lost due to the combustion in the reactor that's needed to sustain the heating. And so you can see here our conifer ground mix, actually we had a very low loss of fixed carbon because, and this again backs up the idea that was a really ideal feedstock in many ways. Whereas if you look at the conifer chip, the medium, where we had really high moisture content, a lot of the fixed carbon in the product had to go to driving the reaction to drive that water off to generate the char. So we didn't have a very good fixed carbon yield there. And the same with the pinyon juniper. The high ash content of the feedstock really led to a significant amount of the fixed carbon being needed to drive the reaction to generate the char that we did produce. This graph shows in a different format, sort of the same result. The correlation between the percent loss of fixed carbon and the sum of the feedstock moisture and ash content is highly correlated. So to the extent that you can manage your feedstock to reduce moisture content and ash content, you will realize a better result in terms of the percent of fixed carbon that you're actually able to bring to market. And we also looked at the heating value and the relationship between that and the percent of fixed carbon. We have benefits with the biochar as far as sequestering carbon in the soil, we also could potentially use biochar as an energy product. You can see the heating values are pretty high. They're near the high end for coal for some of our runs. The other benefit of maintaining a higher fixed carbon in the product is that you have that higher heating value, which can also be put to use depending on the market. So this chart shows some of what we've learned about the estimated labor hours as a function of the sum of the moisture content and ash content. You can see that the pinyon juniper required a significant amount of labor relative to the other feedstocks. The pinyon juniper, which had a high ash content, and then also the conifer, which had a high moisture content. It took a lot of effort to keep that machine running optimally and generating the product. And whereas compared to some of our other feedstocks that had the lower moisture content and or lower ash content, we were able to generate that ton of biochar with a lot less effort. And next we will show you some of our results regarding electricity requirements for this process. We found the average electricity demand was around 12 kilowatts, but that was highly variable. It could vary plus or minus 10 kilowatts within a given hour. We found that from our data, a generator needs to be able to provide about 26 kilowatts of peak power, and it should see a sustained load of around 12 kilowatts based on our testing. So this chart shows that variability, and then we took a look also at to see if that demand, that variability in demand was correlated with the biochar production rate. So if we push the machine hard to try to generate more kilograms per hour, does that directly correlate to increased electrical demand? And it wasn't a strong correlation. So there are definitely other factors at play besides just trying to maximize production rate. Our hypothesis for the high degree of variability in the electrical consumption is that it's correlated to the bed depth within the reactor, and this is our preliminary conclusion after operating the machine and looking at the data, is that you're able to, as an operator, choose to run the bed depth relatively deep, and that is the way you want to run it in certain cases, but that requires the blower to do more work to draw air through the reactor, and also requires the stir motor, which is slowly agitating the reactor to consume more power as it moves the larger bed of chips. And with that, I'm going to turn it over to Mark Severy, who can talk to us about integration and future work.
All right, so I'm going to first start off by describing a few fire hazards we observed during our testing. The first and most major fire hazard was embers emitted from the exhaust stack. After our testing, Biochar Solutions Incorporated, the manufacturer of this machine and also a partner on our project, fabricated a spark arrestor, which you see on the bottom half of the screen. This has currently been installed on the machine in Northern California. It's undergoing validation testing. So we'll have results to come, but we expect that it's going to work quite well. Other fire hazards we observed were dust collection around the machine and dust clouds forming around the reactor. Also, the integrated dryer produced very hot air, which could potentially combust wet chips. And we noticed that the biochar machine exited the machine quite hot at temperatures over 200 C. This table kind of outlines those small hazards, but then identifies mitigation measures, and which are quite simple, which can address these risks and make this machine safe for in-field operation in the forest. So now I want to talk about integrating this system within a larger biomass conversion scheme. This first slide shows basically a flow diagram for the biochar machine. The values shown here are the mean from all of our testing. We see 380 kilograms of feedstock at 18% moisture are converted into 43 kilograms per hour of biochar using about 12 kilowatts of electricity. The feedstock entering the machine is at 18% moisture, which is, as you notice, lower moisture content than that of forest residuals, which are typically upwards of 30 or 50%. And so this large source of waste heat coming off the machine could potentially be used to dry these forest residuals to an acceptable moisture content. Next, we're kind of taking a look at that concept. The heat exchanger installed on the biochar machine exhaust stack was able to capture 80 kilowatt of thermal energy, and applying that to a dryer that we've been testing, we believe we can dry about 560 kilograms per hour of wet feedstock down to 480 kilograms per hour of an acceptable moisture content for the biochar machine. So after using some of that feedstock for the machine, we'd still have about 100 kilograms of dried feedstock produced per hour, and we can potentially find another use for this. And one concept which we've been looking at is briquetting forest residuals, and to produce densified biomass, and this can increase the transportation effectiveness just by increasing the density of the fuel. So if we add this to the flow diagram as pictured on this slide, it will increase the electricity demand up to 21 kilowatts on average. So trying to figure out ways to meet this electricity demand can be difficult at remote field sites in the forest. Typically, we might use a diesel generator, but another option would be to use a biomass gasifier, which we're pursuing as part of our testing in this project. This diagram just incorporates the gasifier to provide the 21 kilowatts of electrical demand. You'll see just a small portion of the dried feedstock is fed into the gasifier, which can provide electricity to 3 processes. As a side benefit, the gasifier also works as the same function, works under the same mechanisms as the biochar machine and produces a side stream of biochar, so we'd actually get a slightly higher biochar yield out of this whole process. And so this system integration concept, we're actually going to be testing something similar on this very biochar machine here in California this summer, except without the briquetter. And this is just a quick shot of kind of our first cut at what this integration might look like. So we're going to be using a dryer to take some waste heat from the biochar machine to dry the feedstock, which will be used to produce biochar. And this gasifier, we purchased a small 20 kilowatt gasifier from All Power Labs, and we'll be testing that machine, hoping to provide enough electricity so this system could be standalone. And so now we're going to cover some of the main challenges we saw throughout all of our testing and kind of what we've described throughout this webinar. We found that feedstock quality has a large influence on biochar quality and also on the operational intensity of the machine. Through some of our testing, we found that moisture contents below 20% and ash contents below 15% kind of are the limit of what this machine can handle while still operating on a commercial basis. We identified some fire hazards, but also provided a list of simple mitigation measures so that this machine can be safe for in-field operation. The electric power we noticed was highly variable throughout the test run and also between different tests. It could be difficult to find enough to power this machine in remote locations, but we're going to be testing a biomass gasifier to see if it's a good alternative to a diesel genset. And lastly, the challenge of integrating this within a larger system to provide power for the machine, but also be able to have a good source of dry feedstock that's an acceptable input. And so to address those challenges moving forward into our future work on this project, we're first looking at addressing the fire hazards, and we've installed the spark arrestor that Biochar Solutions has produced, and we'll be verifying its performance upcoming this next spring. Also, we'll be installing a dryer and gasifier that we'll be testing to see how the system integration concept works. Biochar Solutions, who's a close partner on this project and the manufacturer of the machine, they're working to double the throughput and produce a new machine, which should help the economics in the long run. They're also automating the feedstock input mechanism, which would greatly reduce the labor requirements and operational intensity of the machine. And so that kind of wraps up the main section of data reporting that we had, and we'd be happy to address any questions and open up the discussion. Craig Rawlings from Forest Business Network is going to be facilitating this discussion, but we're happy to answer any questions that you may have, as I see a few coming in the Q&A bar.
Okay, thanks a lot, team. Waste to Wisdom, y'all did great. Tom, Mark, Arnie, Dave, it was great presentations. We do have a couple of questions. We've got one or two questions from one of our attendees. His first question is, the conifer ground, does that mean hog fuel? So, Team Schatz, do you mind answering that?
Yes, the answer is yes to that.
Okay, great. On
that note, sorry to interrupt there, Craig, but one of the nice things about that is it's just a lower embodied energy feedstock, so you're able to, one of the nice things about this machine is that you're able to coarse grind fuel and use it in the machine, and it seems to do well.
Okay. Well, that's great. Thank you for that. The other question that same individual had was, have any of the emission tests of the Biochar solution machine included greenhouse gases? We have, I think it's saying was on one of the slides there.
Yeah, I think we have an appendix slide dedicated to this, so I'm actually going to flip forward to that. And the short answer is yes, that greenhouse gases are emitted as part of the syngas. And before addressing the broader impact of that, let's just first look at this chart. And the x-axis is just showing the amount of combustion air inlet into the flare, and then the y-axis just shows the concentration of those emissions. So you'll see that if you have very clean combustion with a lot of excess air being flowed, you'll have this green line with some excess oxygen, and then the main amount of emissions are only CO2. I think for broader impacts, there will be some greenhouse gas emitted, but overall, the literature on this subject has kind of shown that biochar production and use as a soil amendment can be easily carbon neutral, because a lot of the carbon emissions to the atmosphere is just brought back into the biomass as the trees are growing. So this shows the potential to be greenhouse gas neutral or even negative, since you're sequestering some of the carbon in the soil for a very long time.
Okay. I think the shots team can see all of the questions. I think the shots team can see all the questions. There's three, I believe there's three more there. If you don't mind, just go on through them instead of having Tom have to switch back and forth between me and the shots team.
Okay, we had a question from Jim Dooley. The question is, what data do you have on airflow resistance versus bed depth for the different materials? Very little, unfortunately, and this is something that I'm actually quite interested in. We didn't keep a great record on the bed depth during the test runs, and even throughout each test run, it varies quite substantially, just as small pockets of combustion happen throughout the bed and fall down and change the height and resistance. I've looked quite a bit into literature on this subject and haven't been able to find anything. Biomass is a very variable fuel, and it's hard to estimate the resistance or pressure drop through a fixed bed. So I think this is something that's interesting and is most likely correlated with our electricity requirements. Let's see what other questions we have.
How many gallons of diesel? We were running off the grid in Colorado, so that was not something we had estimated.
Yeah, we do have data. I mean, I guess the consumption of diesel, it depends on where in the life cycle you're looking for that. And in terms of the electricity production for the device, we do have data on the amount of electricity that was consumed by the device, and we can certainly estimate diesel consumption from that. It's not something we've done yet, but it is something we can do. And in terms of the rest of the life cycle, you would have to look at the collection step and the transportation steps to look at the amount of diesel consumed across the entire life cycle, and that's work that the analytical team is engaged in, but they're not finished yet with that life cycle assessment work. So that's a result that we expect to be able to generate in the course of this project, but it's not one that we have yet.
Okay, so we got another question here. There's actually two questions about the flare and exhaust gases. The first one being, what happens to the tars produced in the gasification process? These essentially do not condense, and they'll just exit in the flare. They undergo combustion in the flare and then just exit through the top. They're just basically not collected as they would be in bio-oil production systems. The next question from Rick Bergman: with the waste gas from the biochar machine being flared, is there any possibility of integrating that gas with the syngas from the gasifier for electricity production? I think the short answer is technically that's totally feasible. Just the gasifier and the biochar machine are two commercially available technologies that have kind of been developed for different uses, even though the process is very similar. The idea of using the syngas from the large biochar machine for electricity production is possible, but there's many benefits to having two separate systems because, for instance, when you need to start up the biochar machine and you need some power to begin, you're not producing any syngas to provide that heat. So having a separate gasifier that you can start feeding biomass early in the morning and having the electricity production ready to go when you're ready to start operation on the larger machine. Okay, we got another question. Can this system use sewage sludge as the feedstock? If so, how about drying processes to get it to a sufficient moisture content?
We don't have any experience of using anything other than biomass in this machine. I do believe they use nut shells as well for generating char. My sense is that the volatile content of sewage sludge would be so high that you would not get anything useful out of it in terms of char. Essentially, you'd have a very, very low char production. And the purpose of the machine is to produce biochar. So you want to start with something that has a pretty good fixed carbon percentage. And I don't think sewage sludge is really a great candidate for that.
Yeah, and we got another question from Scott Golden about ash content in the pinyon juniper mix. He asked if we contribute the high ash content from the PJ material to contamination at the logging landing/processing area. And yes, I think just the way in which this material was harvested, they were basically just pulled out of the ground. So there was a lot of soil and dirt entrained within the root system, which were also run through the machine. But secondly, just the nature of the bark on pinyon juniper, it's quite porous and tends to have a lot of dirt and dust stuck in it, just that have blown around. Also, just the environment also that PJ tends to grow in is usually pretty dry and dusty, and that ash tends to get stuck in the bark or into the material itself. So there may be ways to reduce the ash content in PJ, but it may just be inherent to the feedstock. So another question we got is, have we looked at opportunities to condense wood vinegar out of the syngas before releasing it? No, we haven't. We based on some of our experience with bio-oil production, we found it to be pretty costly, and especially when you take into account the amount of contamination that can happen to your filters or your condenser, it can be quite operationally intensive. But also, more specifically to this project, we just haven't been focusing on oil production technologies, and the machines we're testing are pretty much designed for one purpose. Like, this machine was designed to produce biochar at the highest, most efficient rate as possible, I think. So we've kind of been focusing on that issue itself. And almost a follow-up issue with that, a follow-up question to that is, are there maintenance issues regarding tar generation?
One of the practices there for the operators is to, when you shut down production at the end of the day, is to decoke the machine. So you run it pretty hot until you actually empty the reactor, and so then you're drawing. You basically, at that point, you're no longer gasifying. You're essentially drawing heated oxygen, heated air through the process, and that sort of, if you're done regularly, and if you're using feedstock that's of good quality, that's sort of how they're dealing with the tar. There's I'm not sure the maintenance interval for taking the machine apart to manually remove tars from the piping. However, as I mentioned, if with consistent feedstock and good operations, it's not a significant impediment to production.
Okay, another question coming in from Rick Bergman, who heard of problems with spontaneous combustion of torrefied material in super sacks after they've been stored for a month or so. Is this also a problem with biochar collected in drums, or are we monitoring the temperatures? Yeah, so this machine, the biochar auger, is cooled by an external water jacket, which uses a free convection radiator as the heat dump. And yes, we were monitoring the temperatures during our testing, and if they weren't sufficiently cooled when they exited the machine, we would just cool them down with water for safety purposes. I'm not sure if this is typical practice, but one of the things we noted on our fire hazard mitigation slide was to increase the effectiveness of that heat dump so that the biochar is exiting at essentially ambient temperature instead of the high temperatures that we would occasionally observe. Oh. This guy? Okay, we got more questions. We were talking about the contamination in the pinyon juniper. One question was, what was the pinyon juniper contaminated with? Soil, sand, etc. We didn't add any contamination to it. It was just as received, and I believe that there was A, soil, and B, sand entrained in the feedstock material.
Yeah, and small rocks as well.
Yeah, small rocks. Mm-hmm. Another question, how many personnel are required to operate these machines?
It's a one operator machine. And as mentioned, Biochar Solutions is working on automating the feed system a bit more, which is so that the machine will automatically sort of keep the reactor depth at a constant level. So that'll help, but it'll just by the nature of it being high temperature, we think that one operator at least at all times while it's operating is required. But as long as you're careful about your feedstock and as far as keeping the moisture content and the ash content within the specified limits, one operator should be plenty. If you were in a position where you needed to make biochar and you had some substandard feedstock, you might benefit from an additional person to help because it does become more difficult to operate if the fuel is very wet or dirty.
Okay, thanks, Dave. I see two questions coming in about emissions. I guess we've had this slide up and you've had some time to digest it. So the first question is the balance of biochar emissions, nitrogen or water vapor. The balance on this plot would all be nitrogen. These are actually reported on a dry basis, so the moisture content in the vapor was already removed. And is SO2 plotted in ppm? Yes, that would be an alarming amount of SO2 if it was not, but you see there's a little orange arrow where it says SO2 that's pointing to the right vertical axis, and so that's plotted in ppm. Another question about the emissions are the emissions of CO, VOCs, and particulate matter from the flare of any concern? And the answer is, of course, like this machine would need to meet any air quality standards and be permitted as well. What this chart that's still up on the screen shows is that we can achieve these levels if we provide sufficient airflow into the flare, and that the main emission would just be nitrogen, oxygen, and some CO2. We got another question coming in from Joel. It says, does your data provide a threshold for the amount of ash that would be acceptable in the feedstocks? Yeah, we were kind of saying 15%, but it's not really a threshold level. As you saw, we were able to run the Pinyon Juniper, which had 22, 26% ash content. But with ash contents that high, you see that there's degradation to the quality of the biochar in terms of the amount of fixed carbon you're getting out, and then also the amount of labor required to operate the machine significantly increases. There's a lot of tasks that would require shutting down the machine halfway through the day just to clean out slag or clinkers in the bottom of the reactor, which would require some downtime. So we don't really have a threshold level, but as the ash gets higher, the labor requirements increase and the biochar quality decreases, so the economics would not work as well. We are recommending 15% just as a decent number, but we haven't worked through the economic analysis, which would say if there's a more stringent cutoff value. So we got a question from Chad Covert. What are the existing markets for biochar? Is there interest in the market?
And there are multiple markets for the biochar that we're seeing. That the market side of it is not the primary focus of our work, but is a key area of focus for the analytical team. And but just from the work that we've done so far, there is a market for the use of the biochar as a soil amendment. We're seeing that in our region, and have heard anecdotally that there are markets for biochar as a soil amendment in other regions as well. We've also seen that very clean biochar with low ash content can be used as a feedstock for producing activated charcoal material for filtration, and there also seems to be interest in biochar for remediation type projects, although we haven't seen necessarily that a significant market is developed for that yet. I think there is a lot of interest, and a market could develop there. And again, this is the marketing side of things is a significant element of this project, and there's a team led by Ted Bielek that is focused on doing analytical work that includes an element of examining markets for these products.
We got more questions coming in about emissions. Are we measuring nitrogen oxides, for instance, NO, NO2, etc.? Yes, we are. We're not displaying them on the screen, but also our instrument wasn't reporting good data on those values after we came back to the lab and started analyzing the values. So we don't report them here because they're not trustworthy, but our future testing, we've got our analyzer fixed and calibrated and ready to go to potentially measure those emissions in the future.
We have a question about what permitting process, i.e. California air regulations. A good question. We know that that the machine was permitted to run in Branscombe as part of Riffy's project. We weren't involved in that permit process. We will soon be involved in a permitting process for the spring operations, and so we would be. We're not in a great position to answer that right now, but we would be in a few months. So if Scott, if you want to stay in touch, we can feed back the information once we get it.
But certainly the California regulations are the ones that would apply, and so it would need to meet the air quality requirements to be deployed, and that is the process we're working in.
Okay, I see maybe just one more question, and hopefully we can stay in touch with you, Scott, in terms of the air regulations. I saw one of your questions also. But this is coming in from John Field. Rather than adding a supplemental gasification system to produce syngas for electricity generation, why not just use the gas produced from the biochar machine itself rather than flaring it off? And I think I touched on this with a different question, but we're kind of, the 2 points are, A, we're just testing commercially available technologies. This is more of a project to assess what's available in the market and how can it work and how can they work well together. And then more technically, separating a gasifier for electricity generation and the biochar machine adds the benefit of not having to store electricity for startup and shutdown, which could, if you were trying to run it all on one machine, it would require a really large battery bank to meet maybe surges in production and also the startup and shutdown. So for commercially available technologies, it seems best to have the gasifier separated from the biochar machine and have just them focused on providing one task effectively. Do we plan to write a report of our main findings? If so, when will that be available? Also, will these slides be posted to the Waste to Wisdom website? We have a report in the works for our main finding, and I'm not sure how that will be distributed to the larger team and to the public in general.
But it is something that will be available and should be published, I would guess, within a few months. And in terms of the slides, I think we'll let Craig or Tom answer in terms of will they be posted to the Waste to Wisdom website, but I can say that we're happy to share them.
Yes, we will have those posted to the Waste to Wisdom website, waste2wisdom.com. And that's actually kind of a segue, you know, if you all have any further questions or think of anything after the webinar is concluded, feel free to go to the waste2wisdom.com, go to the contact form, you can send us a message. We'll get that answered for you, and yes, look for that. I'll actually be sending an email to you to let you know when the webinar is posted to the website and where you can find that. And it looks like, I believe that's all we had in questions today. Unless the SHOTS team or Craig has anything else to say, I think we can conclude the meeting. Are you all okay?
Yes, thank you.
Okay, great. Well, we really appreciate you all participating today and listening to the webinar. And we do have one more webinar that was mentioned that will be held sometime here in December on the evaluation of economic and environmental benefits from utilizing forest residues. We'll get you some information on that as well. Hopefully, maybe by the time we're able to let you know when this webinar is posted to the website. But anyway, have a great weekend, and we'll see you at the next webinar. Thank you.